Drew this up right here. We have our analog reference signal right here, and we would like to generate a PWM signal that is directly proportional to the analog input right here. And all we have to do is apply some sort of ramp here. It can be, sawtooth, it can be a triangle, it really doesn't matter as long as it's some sort of ramp function. And if we apply this on the negative side of a comparator and our analog signal on the positive side of a comparator, that's all we need. We're going to get our PWM. And this makes sense because as long as this signal is higher than the ramp, it stays on, and the moment the ramp becomes higher in voltage, the output goes low. So, as the ramp goes up and down, it compares the analog voltage to that, and the width is determined by where you are on that ramp signal. So that is quite easy, but why would you even do that? Why would you turn an analog signal into a digital one? Okay, so there's a bunch of reasons PWM is used. The most obvious one is you only switch on and off with PWM. So you do not need to worry about linearity. If you build a transistor amplifier, you can just do hard on and off switching and don't have to worry about creating some sort of linear amplifier. The next thing is it's in many applications a whole lot less lossy. For instance, let's say you want to regulate a DC motor with it. Ordinarily, if you want to get this motor going at half its capacity, let's say it's a 12-volt DC motor and you only want to give it 6 volts, then your transistor has to burn the other 6 volts at whatever current the motor draws, which would ordinarily be converted in heat. Now with PWM, we can just switch it on only 50% of the time, and it has the same effect essentially. And as long as this PWM is fast enough, that means that this reference sawtooth is fast enough, the eyes will not actually notice it, so you can dim LEDs and all kinds of other lights with it, and that's where it's often used. It's even used for music. You can put a music signal right in here, or any kind of audio, and if you choose a high enough frequency, you can use normal switching transistors to get your PWM signal. And all you need to recover an analog signal out of the PWM signal is a low-pass filter. So if you'd low-pass filter this signal right here, you would get an analog voltage that's proportional to our analog input voltage. That's really all the magic to it. And in the setting that I'm going to show you in a moment, I'm using a function generator to generate the sawtooth here. But if you're trying to play along at home and you don't have a signal generator or anything like this, just build yourself something like this. Little resistor here, and capacitor to ground. I know it doesn't look pretty, but this is just a simple inverter. Can be CMOS, TTL, a resistor, and a capacitor. The formula is on the internet on how these relate to frequency, and then you can tap off. I did that wrong. This is going to be an on-off signal. You're going to tap off here, of course, and if you have a operational amplifier, I would use a unity gain amplifier there to tap it off. But anyway, let's move to the workbench and let's have a look at this. Alright, so that's the setup. It's exactly what I showed you on the whiteboard. This right here is obviously our signal generator that's generating the ramp function. In this case, I chose a rectangular signal just because, like I said, you can use a sawtooth, be it a sawtooth up or down, it really does not matter. And I have the MDO hooked up to my setup right here, so that in green we see our analog signal. The yellow is clearly the signal that we're sending into the comparator to compare against, and this purple line down here is the output of the comparator. So what we are expecting is if I increase the voltage by adjusting this potentiometer right here, as the green line rises, we expect the PWM to come on, and when it's all the way on the top, we're expecting this signal to be constantly high. So by the way, I also inserted an LED at the output so that you can visually see how PWM is able to control things like LEDs. So you see the LED coming on there. I And you also see the PWM coming on. And as I increase the reference voltage, the duty cycle for the positive phase increases. And there we go. Now we're constantly positive, and the LED is at full brightness. And if we go back down, we see the duty cycle decreasing. If you look at the LED, see the LED dimming down, and here it's gone right around this point. And that's consistent with what we see on the screen.